I just looked up briefly. I was actually here for the Humboldt colleague in 2010 for the very first time. So that's some time ago, where I spoke about ultra-cold atoms at micrometer distances from surfaces, and that basically relates to what Peter Krüger was talking about previously. I'm from the University of Rostock. I'm a native German, so the only way a native German can become part of the Humboldt family is to get one of those Juzeliūnas fellowships, as Tilman mentioned. And I also received mine more than 20 years ago, which brought me to Imperial College, to the group of Peter Knight, where I got stuck for about 10 years. I was finally let out just before Brexit. And sticking with the geopolitical theme, I just want to briefly show you where actually Rostock is. So I brought this map, which is from the year 1400. And you see here the Baltic Sea. Rostock is over here. It's a Baltic Sea coast town. And Vilnius is over here, so spelled Vilna. So this map actually shows what it says, the extent of the Hansa. What is the Hansa? The Hansa is or used to be the Hanseatic League, which is essentially the medieval precursor to NATO. And that's kind of a good connection, because the reason why I only turned up today was because this conference had been shifted forward because of the NATO summit next week. Okay, so what I'm going to talk about is about something that Noor already introduced, and that is non-abelian geometric phases. And what we're going to do is we're going to actually make them happen in optics. In fact, using abelian gauge fields, that is the electromagnetic field. So that's something that I don't need to remind you of what geometric phases actually are. The famous Aharonov-Bohm effect gave you the very first instance of a geometric phase, but that's actually a scalar. So what happens if you take a charged particle and you bring it either one way or the other way around a magnetic solenoid, where the magnetic field lines are confined to the cylinder here, then this wave function acquires a phase depending on which way you go. So if you go around the loop, that is this full integral here, that acquires a non-zero phase, and that phase depends really how many times you actually circle around this solenoid, and it depends on the flux that is actually penetrating through the solenoidal thing. So it's a scalar phase. It's something that you can measure interferometrically. Of course, what you would like to do is you would like to generalize this scalar phase to some matrix-valued phase, and because matrices normally don't commute, that's going to be a non-abelian phase. That also depends on the order in which you take various loops in space. Okay, so the idea behind it is also fairly old. Actually goes back to the 1980s, to Frank Wilczek as well. And so in that context, this non-abelian generalization is typically known as, or called, the holonomy. So what you do is you assume some degenerate subspace of some Hamiltonian. I'm going to show you one in a second, how we implement it optically. And then what you do is you somehow make happen an adiabatic unitary evolution within that degenerate subspace. And then what you do is you start out with some wave function psi at some time 0, you perform a loop in parameter space, and you end up essentially at the same place in parameter space as you started out with, but your wave function has now changed. And it acquires a matrix-valued phase, which is given by this path-ordered integral of something which you can sort of ascribe to as a synthetic gauge field. That's where my synthetic part of this talk comes in. Right, so this connection, this gauge field, is just the usual derivative of this evolution operated in the basis of these Stark states. So what you would need is, of course, you need somehow to find a degenerate quantum system, right? That gives you your logic states, and then you can somehow define an adiabatic cyclic evolution that gives you essentially quantum logic gates, and that will build you, what Paolo Zanardi would call a holonomic quantum computing, by evaluating these objects here that are quantum gates because they're unitary evolutions of many particle systems, for example. Okay, how would that roughly look like? Now, suppose you had a parameter space that would actually fit on this sphere here, and what would happen is, as usual in for example also general relativity, what you do is, and here this is because people started using props, so I also have to use a prop now. So the usual parallel transport problem is that when you start with a vector, say on the north pole of that sphere, you're parallel transported towards the equator, and then you rotate it around the equator, say at 90 degrees, and go back up to the North Pole, right? Then this vector here, that's essentially our state vector, that has now acquired a phase. And that phase is, of course, the transformation that you're looking for, okay? So let's get rid of this one here. And I'm going to show you in a second how these spheres actually comes about. Now, stop doing that. So the first instance of what you would need in order to find Hamiltonians that possess Stark states and in which you can form an adiabatic evolution is also fairly well known. And this is the Sterile process, the stimulated Raman adiabatic passage, in which in an atomic system with two ground state levels 1 and 2 that are coupled to a common excited state level 3, right? What you do is you basically detune your lasers from the 1-3 transition and from the 2-3 transitions, but at this common 2-photon resonance, the Hamiltonian associated with this three-level system actually has a zero eigenvalue, and that eigenstate corresponding to that zero eigenvalue is just a linear superposition of those two ground states. And then the usual situation is what one does is if you want to transfer a population coherently from one of those ground states to the other, I have this counterintuitive pulse sequence by which I first shine a laser beam over here and then adiabatically turn it off while simultaneously adiabatically turning on the laser beam over here, and that transfers the population from this state over to this state, or of course to any kind of superposition between the two. And I say that has been known since last century, really. So what we are going to do, first of all, there are of course a few sort of implementations that are optically or optical, or at least in systems that are not necessarily single atoms or atom based, in which Sterile was actually invented. So this left picture here is in fact already 10 years old, and that implements a non-adiabatic transfer, non-adiabatic non-abelian phase in a superconducting qubit. And on the right-hand side, that is the first implementation, as far as I know, of a photonic geometric phase corresponding to an SU2 based on polarizations of photons. And you will already notice that if I only work with photonic polarization states, that is the largest unitary group that I can actually generate, because I only have 2 orthogonal polarizations, right? So I can only have a SU2 transformation. Of course, we want to go a step further. And what we're going to do, I mean, not me, I'm a theorist, right? So 2 left hands. But my colleague Alex Samite in our university, what he does is he writes waveguides with a femtosecond laser into little glass chips by actually focusing a femtosecond laser tightly on a particular spot in this glass. That breaks some bonds, and that changes the refractive index locally of the glass very slightly. So the refractive index contrast is only like 10 to the minus 2, 10 to the minus 3 at most. And that means that the modes or the waveguides here, they have a very extended mode profile, because the modes, they leak out quite a fair bit out of these waveguides. But that's exactly what we're looking for, because when you write 2 of those waveguides next to one another, like so over here, you can launch light in either of those waveguides, and then they see the evanescent field from one of the mode coupling over to the other mode as well. And this is exactly what generates essentially a tight binding Hamiltonian or tight binding wave equation. Now, of course, this is all classical at the moment, and the reason for that is that formally, mathematically, the paraxial Helmholtz equation is nothing else than a 2-dimensional Schrödinger equation in first quantization. Right? So anytime you're looking for wave properties, not second quantized, I come back to that, but wave properties in quantum mechanics, it's enough to study the paraxial evolution corresponding to the paraxial Helmholtz equation. So essentially that's what we do. So you have these waveguides written in your glass chip, and you send light through it, and they evanescently couple it over there, and the coupling constant is sort of proportional to the refractive index contrast, and then the mode profiles of these individual modes on the left and to the right. So, and what we can do with that is we can now go one step further than just doing the standard stirrup, that is the 3-level stimulated Raman adiabatic passage, and I call that stirrup plus, because at the moment we are having 3 waveguides, left, right, upper, coupled to a central waveguide that essentially corresponds to the excited state in our artificial atom, if you wish. So the Schrödinger equation, right? So the time derivative on the left-hand side of the amplitudes of the light in those 4 waveguides is just given by this Hamiltonian multiplied by the amplitudes on the right-hand side. Now, what you see here, this derivative here is of course not the time derivative as you would have it in the Schrödinger equation, but it's the derivative with respect to the propagation distance. And without taking credit for it, but my colleague always sort of jokes, in German, the word for time is Zeit, starting with a Z, so that's fine, okay? So now this system here, having now 3 states coupled to a central sort of excited state, now possesses 2 dark states. So, and these are the states basically corresponding to an excitation of the left waveguide, the right waveguide, and here's the upper waveguide. So, I now come back to this picture of the sphere that I showed you previously, where I said, oh, if your parameter space actually forms a sphere, then you have this parallel transport problem or property. Now, what happens here is that these coefficients, these coupling coefficients, S, P, and Q, essentially, if you write them in a vector, in a 3-dimensional vector, right? And then you change these S, P, and Q somehow. And what you want to do is, of course, you want to generate a loop in parameter space. That is, you want to go back from one point here to another point. Basically, that corresponds to the same parameter values. So essentially, you're looking for the tip of this vector of this coefficients here, basically ascribing a sphere somehow. And it turns out that the parameters, that the eigenstates, the dark states in the system are simply the tangent space to this vector here. And that's precisely the figure that I showed you earlier. Okay, so that your dark space actually lives in the tangent space to this vector consisting of these 3 coupling constants S, P, and Q. Okay. So, and then of course, when you start with a particular dark state, you generate this adiabatic evolution, and what you end up is an evolution equation that essentially looks like the non-Abelian gauge field, a synthetic non-Abelian gauge field. The solution, of course, is this path-ordered integral. So, now, of course, if you want to measure something, the problem is that you need a gauge invariant quantity. So, of course, you're using a Wilson loop that is nothing else than a plaquette in parameter space. And essentially, that gives you a number telling you whether your system has performed a abelian or non-abelian loop. So, here's one of those examples. A very simple loop is you change the 2 coupling constants S and P. You leave the coupling to this upper waveguide constant. This is just this Q here. And then you eventually generate essentially a simple SU2 transformation, which is essentially a single qubit rotation, if you wish. So the way you measure this is you initialize the waveguides at a particular input facet Z0 in these dark states, and then you propagate the light through the system, and I'm going to show you how this structure looks like, and then you measure the intensity of the light coming out at the output facets, and at least gives you the magnitude of the Wilson loop. And if you need the phase information, you actually have to do an interferometric measurement, which we haven't done yet. So, but this is how it roughly looks like as a sketch. So you start out at the input facets with the central waveguide being relatively far apart from the left and right waveguides. And what you see here is as soon as you come closer with one of the waveguides to the central waveguide, that increases the evanescent coupling because the overlap between the modes propagating through those waveguides there becomes much stronger. And of course, in that way, as you can probably already figure out, this essentially generates this counterintuitive pulse sequence of two Gaussian pulses that couple the left and right to this central waveguide over here. And this is just a sketch that this evolution here is indeed starting from a coupling S and P equal to 0, and you basically, with these two Gaussian pulses, you form this loop ending up at precisely the same position. So, and again, you initialize at some initial facet. You just shine in either light in the right waveguide or the left waveguide, and you look for the readout. And this is roughly what you would find at the input facet. For example, you start out with everything in the left waveguide, nothing in the right waveguide, and there's a bit of evolution. And this little bit down here, this orange line, is essentially the population of the central waveguide, which is of course almost 0, and it has to be exactly 0 in order to be perfectly adiabatic for the stirrup process to work. But you can actually see that it is, very close to being 0. The entire process is very close to being adiabatic. Just to show you that we can, of course, inject light either in a dark state, in which only the left and right waveguides are populated, but also we can deliberately say that we want to actually inject light in a bright state, in which also the central waveguide will in fact light up. And this is a fluorescent measurement of this entire chip. So basically what you see here, this line here would correspond to the central waveguide, where you can see there is actually no fluorescence coming out of this chip from that particular waveguide there. Okay, so that works. Now, of course, the question is, how adiabatic is adiabatic? Right? I said that in order to stay in this degenerate subspace, stirrup stipulates that you need to be adiabatic as slow as possible, like John Cale slow, essentially. Right? So, of course, we don't have that much time. I mean, the John Cale piece lasts 635 years. So what you're looking for is that this adiabatic transport, in fact, generates a parallel transport in this curved space, as I've showed you before with the ping pong ball. So, but in an infinitesimal change of this dark subspace projector, in fact, defines a metric tensor. It's been known since 1980. And this one here, this G mu nu, this metric tensor, turns out to be actually the real part of a more general quantity known as the quantum geometric tensor. And the imaginary part is this field strength, which of course has this non-commuting part over here, signifying that we are talking about a non-Abelian field, a non-Abelian gauge field. And then of course, once you have a metric, you can basically essentially quantify your diabatic error by looking at the deviation from the geodesic that is generated by this particular metric here. Okay, so that gives us a design strategy, how to minimize this diabatic error, how to make this propagation as adiabatic as possible, given the constraint that the length of our chip has, of course, a finite value. Okay, so of course you can do it also with indistinguishable photons, because everything so far was just with classical light. When I said I exploit the equivalence, the formal equivalence between the paraxial Helmholtz equation and the two-dimensional Schrödinger equation. Now, if you just do it with single photons, then you find a much richer structure, because it turns out that for a given setup, for a given system like this tripod system, there is more than only 2 dark states. So, for example, if you inject only 1 photon, then indeed you only find the 2 dark states that I was talking about previously. But if you inject 2 photons, you end up with a 3rd dark state. So, and this is something that we found here. So you can either inject a dark state with a single photon coming in from in the right waveguide or in the left waveguide, or you can inject 2 photons into the right, 2 photons into the left, or 1 and 1 on either side. So, and with the same setup that classically only gave you 2 dark states, you can now implement a U3 transformation using 2 indistinguishable photons. So, and this is essentially how that would look like in parameter space where you try also to change the parameters adiabatically. Now, when I say adiabatically, I should probably point out what the size of this chips is, because as I said, the refractive index contrast is not very big. The chips are actually very long, about 15 centimeters long, and you can implement one of those non-abelian geometric phases, which is of course not really what you want. Is not really miniaturizable. So then, of course, you can get away from actually using adiabatic transformations to non-adiabatic but cyclic transformations, which makes your chips much, much shorter. And this is also what people in Hong Kong, Guangkong Ma and his colleagues have done, where they actually used a sequence of these non-abelian gates to actually show braiding of light. There's non-abelian braiding with, I think, 5 different sort of strands, where they could show the non-abelian character of these transformations in there. So basically, this is now in a realization, not in a Floquet-driven basis, but it's just really in an ordinary optical basis. You just propagate the light through it, and you see what comes out. And the way in which the braids work is really just by engineering the sort of the local properties, the local overlaps between the wave functions coming out of these individual modes. Okay, now there's an interesting sort of theoretical conundrum in there, and that is, once you start talking about the single photons, the indistinguishable photons, and you realize that you stick more photons in your system, and it seems as if the entire structure, the entire unitary group, becomes larger, the one that you can generate. The question is, of course, is there a framework in which you can describe that properly, and B, is there somehow a limit to how many photons I can inject into the system before I, kind of saturate the dimension of this transformation that I can achieve? So, for the first question, there is an operator framework for these non-abelian geometric phases, which is basically turning this entire theory on its head by not looking at the modes or the eigenstates that are generated in the system, but at the operators generating the transformations. And what you find out there is something, it looks perfectly trivial, that if you look in this operator framework, you can figure out that you can make all linear optical elements that you try to create in order to generate linear optical networks that are used for, I don't know, machine learning using optics. They can be made geometrically robust simply by adding a simple waveguide in the middle. So normally what you would say is, in this integrated optics, you have these 2 waveguides that would sort of give you, for example, a beam splitter, which is, you have to be fairly precise with manufacturing this beam splitter in order to have like the perfect beam splitter ratio that you want to achieve. And it turns out, to make that robust, you just add this waveguide in the middle. You go into this adiabatic, or in the non-adiabatic but cyclic operation regime, and everything that you would like to do with linear optics can be made geometrically robust simply using these non-abelian geometric phases. Now, to the second question, how far can one increase the dimension of this holonomy group by injecting more photons, indistinguishable photons? And it turns out that there is sort of a limit, and that is given by sort of the Ambrose-Singer theorem, by which we're saying that if I look at this field strength, this non-abelian field strength, the number of linearly independent components in fact give a lower bound on this dimension, and it turns out that this dimension does not grow as fast as you would like. So it turns out that even for very large numbers of photons and very large sort of networks of graphs, we couldn't even figure out, or we couldn't even get any transformation bigger than a U4 for even large photon numbers. So injecting more photons doesn't always help, but it depends on the Hamiltonian itself. Now, I just want to summarize very briefly. We did get non-abelian geometric phases using abelian electrodynamics. And the reason why we achieve these non-abelian properties is just due to interactions, right? And the geometry in which these interactions happen. So we have this geometric evolution as a unitary evolution of the quantum state, and that, as a side product, if you wish, gives us a robust implementation of linear optical elements, linear optical quantum computing. So, and of course, we can try to implement larger unitaries to get one step closer to some holonomic quantum computation. And we could even try to use these Wilson loops that we already measured as building blocks for the simulation of lattice gauge theories. And with that, I need to thank, first of all, the students who actually did all this work. That's my PhD student, Julian Pinske, and Alex Samait's experimental PhD student, Vera Neef. And then I would like to thank you for your attention and Gediminas for organizing this fantastic conference. Thank you very much.
So thank you very much, Stefan, for such a nice talk. Questions? Yeah?
So how do you realize complex matrix elements? How do you realize complex matrix elements in your Hamiltonian?
So, very good question. So Alex Samait would say, "Don't ask me about this. I don't want to do it." There's several ways of doing it. You could try to change the propagation speed of one of the waveguides, and if you go into a rotating frame, that essentially contributes a phase to the off-diagonal element. So that's one way. That's one way of doing it. That is not necessarily very robust. But I mean, you can still, for example, try to use like oscillating waveguides, basically like wiggling waveguides in order to create these kind of structures. So, for me as a theorist, of course I like to have these complex phases because that gives us a much richer structure and much more freedom to play with. But the experimentalists, they always sort of bring me back down to earth and actually say, Stefan, can we just do something simple first? So in principle, it is possible, and I've seen it, but it's not. So the control of these phases thus far is not as perfect as you would like to have it.
Then at some point you also mentioned that you want to use kernel linearities, but when you are nonlinear and you are at the single photon level,
Here, what I was the only thing why we use this canon Hamiltonian here, we are not using it at the moment. The point we were trying to make here, I haven't really talked about it too much, and that is that it depends on the Hamiltonian how many dimensions of a holonomy group you can actually generate by using multiple photon states. That is, the degeneracy of your Hamiltonian depends, of course, on the Hamiltonian itself. And a particular example is this two-mode Kerr Hamiltonian, which turns out to possess, of course, degeneracies. But these degeneracies, they do not increase overall bounds as you would like to have them when you increase the number of photons in them. But we only found, at least numerically, there's no proof yet, no analytical proof, that this dimension of the holonomy group generated by the two-mode Kerr Hamiltonian increases beyond like the dimension of 16, which corresponds to EU4. We are not trying to use it experimentally at the moment.
Okay, fine. Okay. Fine, thanks.
Yep. So thank you. So actually, maybe let me ask you this question, because your dad already gave questions previously. So to another speaker, so some conservation. And actually, so my question is, you have it. Maybe I will give you also opportunity. So since it is the last session, we can take exactly. The last
You're
talk.
The organizer. You ask the last question.
Yeah. So So basically, it's in atomic knowledge is tripod, like you have 3 levels, it's coupled too. But it is known if you have a tripod and if you have real Rabi frequency, in your case it's these couplings, your gauge field is abelian essentially because it has only one component, Fy. So first of all, my comment is would be not completely fair to call it non-abelian, but the question is related. If you have this go to 2 photon space, you have already 3 states. Maybe you go to non-abelian something with increasing.
So that goes back to what Jacobo actually asked about the having to actually generate matrix elements or coupling constants that are actually complex. Right? You're absolutely right. So it is a sector in the I forgot the correct phrasing. Because you're talking about a sigma y, basically a Pauli transformation, that necessarily is of course non-abelian. But what is sufficient to show is that if you generate 2 of those holonomies, and you can generate 2 of those that are non-commuting, then you can show that you have a non-abelian situation here. So you're absolutely right. If I only show you one example for one particular realization of one particular holonomy, you can construe that as being abelian. If I show you 2 of those, like U1 and U2, and they don't commute, then I can construct any non-abelian situation by concatenating them. Right? So, and the concatenation is the one that we just started to implement by using this non-adiabatic but cyclic evolution, which makes the chip that we need actually much, much shorter. So at the moment we are able, Alex Samite is able to have to the extent of something like 7 of those transformations, basically consecutive one after the other, that are all non-commuting, right?
Okay.
I don't know whether this answers your question, but
okay. So we can maybe continue discussing later in the break. So Odette, please.
So I still have a chance. Okay. So thank you. I guess maybe to follow up on Gediminas, can you show the Young-Bunkster relation for the braid group?
People have shown that.
Okay. So,
yes.
but I mean, will it manifest experimentally as that?
Yes, I believe that is the one in this paper here.
I see.
That is the one. So
but
that's
you
the
would need
idea.
3 braids that are. You would need 3 braids.
Yes. You need 3. Yes, exactly. You need 3 strands, right? And then what you do is you just show that. I mean, what's the Young-Baxter equation doing for you? It shows that if you for example flip or interchange the first 2 braids, then the second and the third, and then you reverse the order, then what you get is not the identity. And this is what they've shown.
I see.
Right? Okay. So that's been shown as as I say, this system here actually has shown this Young-Baxter relation with, I think, up to 5 strands, and then basically just braiding of like neighboring things. So that is indeed, it's just based on the Young-Baxter equation, absolutely.
Okay, so thank you very much. So we can continue again during the break. And now let us thank Stefan and all the remaining speakers.